Hi, and thanks for watching. I'm here to explain a new paper that takes on one of the toughest open questions in modern physics, one that's been unsolved for more than 50 years. It's called Proof of the Yang-Mills Mass Gap in 4 Dimensions. So what is the mass gap, really? In simple terms, it asks whether the vacuum of a pure Yang-Mills field, basically the mathematical foundation for the strong nuclear force, can ever be truly calm. If you nudge that field, can it ripple with almost no energy, or is there a hard energy floor that keeps it stable? That floor, if it exists, is the mass gap, and proving it is one of the official Clay Millennium problems, the big unsolved puzzles of physics and math. Why has this been so hard? For half a century, every approach ran into the same walls. First, the gauge problem. To describe a Yang-Mills field, you have to pick a gauge, kind of like choosing coordinates for invisible directions in space. But that choice can create duplicates in the math and break a key property called reflection positivity, which is what makes quantum probabilities behave like real ones. Once that breaks, the whole structure collapses. Second, the continuum problem. Simulations work great on a discrete lattice, but getting from those building blocks to a smooth, continuous spacetime without losing mathematical control is insanely difficult. Third, the mixing problem. In an interacting non-abelian field, it's hard to prove that distant points eventually stop influencing each other, that information fades instead of echoing forever. And finally, the closure problem. Even when researchers got parts of the puzzle right, they couldn't tie everything together into one self-consistent quantum theory with a provable energy gap. So what's new in this paper? How did we solve it? This proof follows a completely different route, one that never breaks the core symmetries or the math that keeps the theory physical. Step 1, stay gauge invariant. We only measure smeared local invariants, basically small, blurred quantities that are completely independent of how you choose a gauge. That way, everything we measure is physically real, not just a coordinate trick. Step 2, keep reflection positivity intact. We build a finite bridge from the lattice version to the smooth continuum that keeps the mirror test for probabilities valid at every step. Nothing breaks, nothing approximated away. Step 3, show fast mixing. Using mathematical tools called log-Sobolev inequalities, we prove that small regions of the field quickly forget their initial state. Then, using a clever two-scale argument, we extend that to the whole space. Translated, the field stabilizes itself, faster than disorder can spread. Step 4, turn that mixing into a real mass gap. A chessboard-style combinatorial argument turns the measured string tension into exponential decay of correlations, basically showing that distant regions are almost independent. And finally, we apply a construction called Osterwalder-Schrader reconstruction that takes those decays and builds a proper quantum Hilbert space with a single vacuum state and a non-zero energy gap. Okay, so let us talk about why this worked. Most earlier attempts either fixed a gauge and broke positivity or relied on approximations that couldn't be closed. Our approach stays fully gauge invariant the whole way, keeps reflection positivity exact, and tracks every constant at one fixed physical scale so anyone can check the math line by line. The final result? If this holds up under review, it means that pure Yang-Mills theory in 4 dimensions, at theta equals 0 for any compact simple gauge group, has a positive mass gap. That's a stable vacuum, an exponential decay of correlations, and a finite minimum energy needed to make a disturbance. It's one of the hardest problems in theoretical physics, and now, for the first time, we may have a clear gauge-invariant path through it. We invite you to read it, verify it, and try to stress test it yourself. The Zenodo link is below. Thanks for watching, and thanks in advance for your constructive feedback.